All right, so I'm going to walk us through a little lesson on volumes of solids of known cross sections. This should really say volumes of solids with known cross sections. And so let's start with a few basics. First of all, we need to make sure that we know the area of some basic shapes. So for instance, we need to know the area of a square. Let's just call this x for now. So we know that if we have a square, of course, we know the area of that is x squared. We also need to know how to find the area of a semicircle. Maybe this is x, so therefore the radius would be x over 2. So this would be x over 2 squared times pi, right? That's pi r squared. But we'd also have to divide it by 2 because it's a semicircle. So this would end up being pi times x squared over 8, I guess. No need to memorize that, but we know how to find the area of a semicircle. We also need to know how to find the area of an isosceles right triangle. If this is x, isosceles right triangle, meaning two sides of the same length, has a right angle. Of course, this is just going to be x squared divided by 2. And I guess we also need to know how to find the area of an equilateral triangle. So if this is x, and this is x, and this is x. Well, remember, if we zoom in on one half of this equilateral triangle, so if we zoom in just on this little bit right here, half of it, then we get this triangle right here. That's a 30, 60, 90. So that's 30 degrees. This would be 60 degrees, and this would be x over 2. Remember that if you have the short side next to the 60 degrees, the long side is that times root 3. So this would be x root 3 over 2, and this would be x, which is what we already know. So that means the height of this equilateral triangle is x root 3 over 2, which means the area of this equilateral triangle is actually square root 3 over 2 x squared. Again, not something you necessarily have to memorize, but it can be useful. So these are things that we already know. So let's move into calculus. So the basic idea is that we're going to have some sort of region in the xy plane. Okay, so let's say that, just for the sake of it, let's just say that it were this right here. And then we're going to stack these shapes on top of this region. So for instance, that right there is going to be the base. Let's say if we were going to stack squares, that would be the base of a square that looks like this. And this right here would be the base of a smaller square that looks like this. And this would be a little bit larger square. And those would be coming out of the screen at you. So if this is x and this is y, I can try and draw this in 3 dimensions. So let's see if I can remember how to do this. We'll let that be our z. This is going to be our y-axis here. This is going to be our z-axis, and the x-axis comes off like this. So you can see that this is now the XY plane is now right in here. So I've sort of taken it and rotated it and laid it down so I can draw in 3 dimensions. So this function right here would look something like that, right, in the XY plane. And these little rectangles that I drew would be right here, would be one of them. Another one would be right here, and another one would be right here at the start, something like that. And what I'm saying is we are actually going to stack squares on top of these this region, and they'll be different sizes because they're determined by how big the how far the function is from the axis. And we're going to get some sort of interesting 3-dimensional shape that if we cut it anywhere, we're just going to get a square. But it makes sort of an interesting 3-dimensional shape. So that's the basic idea. Of course, if we didn't want to stack squares, we could stack semicircles, for instance. So let's say we had semicircles. Maybe that semicircle would be like that, and this semicircle would maybe be a little bit smaller, and this one would be even smaller still, right? So in 3 dimensions, we had our y-axis here. And for those of you, looking forward to taking multivariable calculus, you can get better at drawing in 3 dimensions. So you have your x, y, z. And I'll draw my function again with something like this. There's one rectangle, here's another, here's another. Okay, we're going to stack semicircles on top of this thing now, and that's going to make a different three-dimensional shape, right? So kind of looks like a, I don't know, I'm not really sure what that looks like, but maybe a gazebo, not a gazebo, a greenhouse or something. But it's definitely going to look different than this one. Okay, so that's the basic idea. We are taking um, regions in the XY plane, and we're going to stack known cross sections on top of them. So it could be an isosceles right triangle. It could be a semicircle. It could be a square. It could be a rectangle, maybe that's defined in some way, or it could be an equilateral triangle. But it has to be something that has a flat base because we're going to stack it on top of a flat area. So it has to be something with a flat base in general. I mean, we could even do hexagons if we wanted to get fancy, but for now, we'll just kind of stick to these basics. So let's look at some examples. All right, first thing we're going to do is sketch. The base of a solid is the region enclosed by this function and y equals 0. Y equals 0, that is the x-axis. Cross sections perpendicular to the x-axis are squares. Okay, that's important. Now you'll notice all of these cross sections that I drew here are perpendicular to the x-axis, but theoretically we could do perpendicular to the y as well, and that would give us a different type of three-dimensional figure, but these are all perpendicular to the x-axis. Okay, so we need to find this region. So let's figure out where this intersects the y-axis. So if I take that and set it equal to 0, take this function and set it equal to 0, I get 0 equals negative 1/9 x squared plus 4. Subtract 4, and okay, this is fine. Multiply by negative 9, I get 36 equals x squared. So x equals plus or minus 6. That is just helping me to sketch this thing in 2 dimensions. So okay, plus or minus 6. So here is my graph. This is the x-axis, which is y equals 0. Here is, let's call it 6, and here is negative 6. Negative 1/2 x squared plus 4 has a y-intercept up here at 4, and so it is going to look like a quadratic that opens down. And that is the base of a solid. It's the region enclosed by this graph, which is y equals negative 1/9 x squared plus 4, and y equals 0, which is the x-axis. So that's my region. Cross sections perpendicular to the x-axis. So the first thing we're going to do is we're going to draw a cross section that is perpendicular to the x-axis, which looks like that. That is a cross section perpendicular to the x-axis. Of course, if we were just computing area, we would just add up a bunch of those little rectangles. But instead, what we're going to do is we're going to stack a square on top of that. So a square is coming out of the board, right? So it's going to kind of come out. I'm not going to actually draw this here, but it's going to come out of the board like this. Well, I guess I could draw it like that. So we've got a little kind of three-dimensional thing coming out of the board and just drawing it in perspective there. And we want to figure out what are the dimensions of that square? So let's draw the square. That square is there. Well, one base of the square is just the top minus the bottom, which in this case is just that function. So that's just negative 1/9 x squared plus 4. But it's a square, so that means the other side also has to be negative 1/9 x squared plus 4. Okay, so that means this is kind of like dealing with discs and washers. If we take the area of this square and we multiply it by a little thickness, which would be dx, right? Then we should get a little piece of toast that has a certain amount of volume, a little square coin, I guess, if that's such a thing. And we will end up with the volume. And then if we add up all of the squares, from one side to the other, then hopefully we'll get this three-dimensional volume. Okay, so let's see here. The area of this square, a of x, would simply be negative 1/9 x squared plus 4 all squared. Now that would be the area of the square. Now if we want the volume of a little piece of toast, we would have to multiply that by dx. And so we can see that the volume of this entire thing, we would just integrate it from -6 to 6 of our area, which is our cross-sectional area, which is -1/9 x squared plus 4 all squared dx. And that should give me the volume of this solid. Now, just because I would like to kind of get a sense for what this looks like a little bit better than I have, I'm going to draw it in 3 dimensions. Okay, so by the way, if you're wondering how to draw things in 3 dimensions, what you're going to do is you're going to start by drawing just essentially a right angle here with your this is going to be your y-axis, this is going to be your z-axis. And then the x-axis is going to come off about at a 45. I like to have it, I guess that's not quite a 45 because a 45 would be more here, so I like it to be a little shallower or whatever when I'm drawing it. And that would be my x-axis. X, Y, Z. Okay. So again, I'm going to draw the function. I guess I actually need to go in reverse for the x-axis. So it goes back to -6, and it comes up to 6. So it looks something like this. That's the function, the xy plane. And then what I'm going to have is I'm going to draw perpendicular to the x-axis. I know that doesn't look perpendicular to the x-axis, but in perspective it is because it's parallel to the y-axis. It took me a long time to kind of figure out how to draw these things. I got kind of actually some bad grades on tests because my drawings weren't good enough in college, which was kind of annoying to me, but whatever. We move on, am I right? Dr. Thompson can, I don't know if he's still teaching, but anyways. Okay, so anyways, I'm drawing squares on top of this thing. Of course, down here, they're going to be very, very tiny squares. This thing almost looks like a square, like pea pod or maybe like bananagrams or something, although I'm not sure that's squares. And we can kind of connect these dots if we want to get a good sense for what this thing looks like. You know, it's going to look something like that. Pretty good drawing. Okay. But in general, what we want to think about is when we're finding these areas, you're going to integrate from A to B. You're going to find your cross-sectional area, which is going to be the area of a square or a rectangle or triangle, semicircle. And then you are going to essentially integrate that cross-sectional area from A to B. Now, that's basically what we were doing before. We were integrating from A to B of pi times r squared dx, right? But that, again, pi r squared, that's the cross-sectional area for a circle. Now we're just generalizing to allow us to do different types of shapes that have flat bottoms. Okay, let's look at number 2. The base of a solid is a region bounded by the x-axis, x equals 9, and y equals root x. Okay, let's graph it. This we should go a little bit faster, I think. Okay, bounded by the x-axis, x equals 9. X equals 9, let's say, is here. And square root x. Square root x looks like this, right? So, whoops. So let's go ahead and hit that region right there. So this is x equals 9. That means this is going to be y equals 3 because that point is 9 comma 3. And that is the region. Okay, cross section is perpendicular to the x-axis. Boom, perpendicular to the x-axis. There's a cross section perpendicular to the x-axis. Are rectangles, okay, whose height is half the base. Okay, so I've got some rectangles coming out of here that are going to be shorter than they are tall. Okay, the largest rectangle is going to be here at the end because that's where the function is the tallest. And the smallest rectangle is going to be down, you know, down here where you're not going to have any rectangle at all because it gets down to 0. So this rectangle, I'm going to draw it out. So here's my base, and I know the height is half as tall. Well, the base of this rectangle is just the value of the function, which is the square root of x, right? Because that is essentially this distance right here. That's the square root of x. And that matches up to this. And the height of this rectangle should be half of that. And how do I know it's half? Well, because that's what they told me. They said it's half the base. So this would be 1/2 root x. So that means the cross-sectional area of this little rectangle is going to be 1/2 root x times root x, which somewhat obviously is just x over 2. So if I wanted to make this thing into a 3-dimensional little sliver, you know, or whatever, it's not a great drawing, but whatever, with the thickness of dx, then I would have x over 2 times dx. That's kind of a volume of a little slice. So now I simply need to integrate it from 0 to 9 of my cross-sectional area, which is x over 2 times little dx to give it a thickness. And that is going to give me the volume of that shape. Again, if I wanted to draw it in 3 dimensions, here's my z-axis, here's my y-axis, here's my x-axis. This thing looks like this, sort of. Okay. And then I am going to, oof, that was bad. That line has to be parallel to the y-axis, something more like that. Okay. And then I'm stacking rectangles on top of this that are going to be a little bit only half as tall as they are wide. Okay, so something like that. So it's kind of a similar shape, but a little bit more squat, I guess we can say that. Okay. Okay, moving on. Base of solids region bounded by this and this. Cross sections perfectly the x-axis are isosceles right triangles. Great. Isosceles right triangles. By the way, this is a half square. Now, I probably should have said something like with a leg in the XY plane or something. So we know that it's not sitting on its hypotenuse, but we'll just assume that that's what they meant, or that's what I meant, I guess. So, okay, great. Let us sketch this friend here. 1 minus x squared, 1 minus x squared, and y equals 0. Y equals 0 is the x-axis. Okay, so x-axis. 1 minus x squared looks like this. Of course, it has zeros at -1 and 1, has a y-intercept at 0, 1. So that's fine. Cross section is perpendicular to the x-axis. Perpendicular to the x-axis right here. Okay, that's lovely. Are isosceles right triangles. So coming out of this thing is going to be, and it could go either way. I don't know if it comes up like this and goes this way, or it could come up like this and go that way. Ooh, that was not a good drawing. That was very bad drawing. Yes, but it would come up some distance and then come back there. I actually think that's a little bit harder to draw, so maybe we'll go with the other way. But in any case, we're getting, uh, yeah, how does that look? Anyways, we're getting equilateral triangles that are coming out of the screen or the board or the paper like so. Right, and they're going to look like, like this, whatever. Okay, I'll just kind of mess these up a little bit, but it looks like that. Let's draw that equilateral triangle. Equilateral triangle. I encourage you to draw these cross sections. Okay, so right angle, the base is just the function in this case, which is 1 minus x squared. 1 minus x squared. That right there corresponds to this right here, which is just 1 minus x squared. And then this is also 1 minus x squared because it's an isosceles triangle, and that corresponds to this right here. Okay, so essentially we've got a little right angle there. And this is also 1 minus x squared. So the area, cross-sectional area of this little friend is 1 minus x squared all squared, but we need to divide it by 2 because it's a triangle. Done, okay? Now we need to integrate this from -1 to 1. We're going to add up all our infinitely thin equilateral triangles, and we'll have 1 minus x squared all squared divided by 2, and dx gives it the little volume, and we are good to go. Do I want to draw this in 3 dimensions? You bet, because worst case scenario, you can just skip this. But of course I do. I need my x-axis to go into the negatives as well. Okay, it goes something like that. It looks kind of like a semicircle, but it's not because it's quadratic. And I have cross sections that are perpendicular to the x-axis, and on top of them are sitting equilateral triangles like so. Oh my goodness, wow. That's good. That is good. Okay, equilateral, smaller ones down here because the function's not as tall, smaller ones down here. And you're going to get something that's popping up like that and around like that. So it's going to be some sort of almost like a quarter sphere type of thing in some ways, but it's not, but that looks kind of like that. Okay. Of course, can you use computers to visualize this perfectly? Of course, right. But I mean, there's no school like the old school. Am I right? Am I right? Yeah, I'm right. Okay. But mostly I'm wrong, to be honest, but whatever. Okay, two more. Oh, thank goodness. We have one that is perpendicular to the y-axis, so we can practice that. That's good. Because all the rest of these are perpendicular to the x-axis. My goodness, these are looking good, although it's looking a little like patriotic or something, which is interesting. But I guess it could be any number of countries. Anyways, it's fine. Let R be this region in the first quadrant, bounded by, enclosed, excuse me, by this function, y equals 0, x equals 0. Region R is the base of a solid. Okay, so this is the region R right here, right? Because that is bounded by the xy axis and that function, okay? Cross sections perpendicular to the y axis are rectangles. Okay, whose bases lie in R and whose height is y? Boom, perpendicular to the y-axis now. Okay, so now remember this is a little change in y dy, so we're going to be integrating with respect to y. And we've got rectangles coming out of here. Now I'm really challenged because I need to come out, a certain distance, where the height is y. So at this point, the height would be, 5, I guess, because that's the y value. But down here, whoopsie daisy, down here, the height would be 0 because the height is 0. And up here, our rectangle would be not very wide, but it would be very tall because the height would be 10 because that's the y value. This is going to be a very weird beast, and I'm finding it hard to draw. So we're not going to worry too much about that. We are going to worry about this being perpendicular to the y-axis. And I'm going to label that with our little red thing here. And that is going to now match up with a rectangle. So there's the base of the rectangle. And the height has to be y. So the height is y. And this right here needs to be something in terms of y, right? This needs to be like a g of y. No, not g of y, g of x situation that's going to be in terms of y. So we need to solve this equation for x. Anytime you are integrating with respect to y, which we are because we have a little change in y dy, and we're moving from 0 up to whatever that value is there, which looks like 12, we need to solve for x. So let's divide by 4. Let's square both sides. We get y squared over 16 is equal to 9 minus x. Let's add x, subtract y squared. We get x equals 9 minus y squared over 16. So this base right here, which you can label as red, is the length of that function, which is 9 minus y squared over 16. Okay, so what's the cross-sectional area of this thing? Well, the cross-sectional area, A of y in this case, is the base times the height, and then we'll have to multiply by dy so that it has a little bit of thickness. Remember that this right here is going to be however far it comes out of the board, right? So it comes out of the paper like that. So we would now integrate from the lowest y value, which is 0, right down here, and then all the way up until we get to the top y value, which is 12. And our cross-sectional area is, I'm going to multiply this through just for fun, 9y minus y cubed over 16 dy. And that is going to give me the volume of this beast. Do I want to try and draw it? Yes, I do. So this is x, this is z. No, that's z, that's y, and here is x. Can I draw this? I think probably not, but there's no harm in trying. Now, oh boy. Okay, so this thing starts up here at 12. It kind of, basically just, whoopsie daisy, basically just, curves down like this. Now my cross sections are now perpendicular to the y-axis. So they're going to be drawn like so. And the height is going to be very low down here. And then it's just going to increase gradually until we get up to here. By the time we get up here, we should have quite a height. It should be quite a height because it's the y value and the y value is increasing. Here, it's going to be lower because the y value is smaller. In fact, the top of this thing is just going to be kind of a nice roof because it's going to be getting taller as the y value increases. So it's actually going to be kind of a nice looking thing, and I'm not too displeased with how this thing looks. I'm not sure if you are, but anyways, it's going to get taller up here because the y value here is 10, so the height has to be 10, and the y value down here is 0, so the height has to be 0, and the y value here is 5, so the height has to be 5. So we should just get kind of a very neat increasing roof here, which I think is kind of nice. Okay, interesting. Okay, last one. I wonder if you're still here. So, congratulations. Congratulations. If you made it to number 5, and you will receive a special commendation, maybe a reward, some sort of prize to go with it in class. You never know. You never know what you can get from sticking it out to the end. Okay, so we'll see. Okay, but let me know because I'll know if you got to this point. Let R be the region of the first quadrant. Oh, it's the same graph. But now we are going to take cross sections perpendicular to the x-axis, and they're going to be semicircles. That's what I like to hear. So what are we going to do? Oh my goodness. Perpendicular to the x-axis. Let's draw a little cross section. I like it right there. Okay, and what are we gonna have popping out of the graph? Well, out of the graph, we're gonna have semicircles coming out like this. So we're gonna have some semicircles coming out above. This is gonna make a nice sort of I don't know, cornucopia looking thing or whatever. So that's fine. Okay, good. So let us draw our cross-sectional area. Okay, that is the base of a semicircle. Ba, 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 ba. And this diameter here is simply the function, which is 4 times the square root of 9 minus x. Remember, we're integrating with respect to x because this is dx. And we're going to slide these slices from 0 to 9. Okay, that means the radius of this little friend is 2 times the square root of 9 minus x, right? Because that would be half of this. So that means the area of this semicircle is pi halves times r squared. Why is it pi halves and not pi? Because it's a semicircle. It's not a circle. It's half of a circle. So that is going to be pi halves times 2 root 9 minus x all squared. That is our cross-sectional area. Let's simplify that to pi halves times 4 times 9 minus x, right? Because if I square 2, I get 4. If I square root 9 minus x, I get 9 minus x. Yes, okay, and so that simplifies, hello, to 2 pi times 9 minus x. Great, that seems good. And that is my cross-sectional area. So if I want to find this volume, I am simply going to integrate from 0 to 9, right? Going from 0 up to 9. And my cross-sectional area, I'll pop the 2 pi out front, and then I'll have 9 minus x dx. Done. Do I want to graph this in 3? Oh man, I thought you'd never ask. Here's y, here's x, here's z or z. Beautiful. Okay. And what does this thing look like? It looks something like that. My cross sections are now perpendicular to the x-axis, so they look like this. They have semicircles on top. The biggest one is there. Then they get smaller, although my graph doesn't really look like that, but they should get smaller. And you're going to get this sort of cornucopia looking thing, which those of you who are artists are going to be able to do some interesting shading maybe, and figure out how that didn't help at all, but that gives us a nice flat bottomed thing. Okay, my goodness, that was fun. It's probably longer than you wanted, but again, if you made it here, you will receive a special commendation in class. Does commendation have two M's? I think so. Commendation. And you might even get, some sort of, I don't know, baked good or something, or a piece of candy or something. I don't know. We'll see. But you should ask about it in class. Okay.